Half a billion years ago, in the deep waters of the Cambrian period, a strange and terrifying creature emerged, Anomalocaris. With a body stretching nearly 3 feet long, a pair of spiny front claws, and a circular tooth-like mouth, it was considered the dominant predator of its time. But here's the strange part. This monster wasn't discovered from a complete skeleton. Instead, it was found as 3 separate fossils that seemed to have nothing to do with each other. For decades, scientists believed they had found 3 different species: a shrimp, a jellyfish, and a sea cucumber. It wasn't until nearly a century later that the truth was revealed. All those fragments belonged to one single animal. So what exactly was Anomalocaris, and how did it become the ocean's first nightmare? Today we'll uncover the secrets of the ocean's first apex predator, Anomalocaris. But before we begin our journey back in time, let us know in the comments where in the world you're watching from and share some of the unique fossils found in your country. The story begins with a great misunderstanding. Initially, scientists found 3 distinct fossil fragments from the Burgess Shale in Canada. The first piece was a pair of spiny limbs resembling a headless shrimp and was named Anomalocaris, meaning abnormal shrimp. The second was a circular disc believed to be a type of floating jellyfish and was called Petoia. The third was a flattened body, mistakenly identified as a sea sponge or sea cucumber, and was named Lagania. For decades, scientists believed they had discovered 3 separate species belonging to 3 entirely different animal phyla. This illustrates the immense difficulty in deciphering an era of evolution so alien to us. Scientists tried to fit these bizarre puzzle pieces into familiar modern animal groups, revealing a natural human bias when faced with novel body plans that have no direct living descendants. The backdrop for this story is the Cambrian period, an era spanning 541 to 485.4 million years ago. It was a world of shallow, warm oceans with an atmosphere containing significantly less oxygen than today. The key location for the discovery is the Burgess Shale in British Columbia, Canada. This is a special type of fossil site known as a Lagerstätte, where soft-bodied organisms are preserved in extraordinary detail. Sudden mudslides buried entire marine ecosystems, preserving delicate features like internal organs, eyes, and soft tissues, something that rarely happens in the fossil record. The first fossil fragments of Anomalocaris were collected in 1886 by geologist Richard G. McConnell and described by Joseph F. White-Eaves in 1892. In the early 1900s, Charles D. Walcott, the pioneer of the Burgess Shale excavations, found more specimens, including the jellyfish Petoia and sea sponge Lagania, but he also failed to recognize their connection. The unique preservation conditions at the Burgess Shale created both the mystery and the solution. The sudden burial separated the body parts of these soft-bodied creatures, but also preserved them so perfectly that scientists could later put the full picture together. For years, scientists reconstructed these fossils as 3 separate creatures. Anomalocaris was believed to be a crustacean due to its shrimp-like shape. Petoia, with its circular structure and central opening, was thought to be a jellyfish. Meanwhile, Lagania was classified with other invertebrates, such as sea cucumbers. However, in 1985, a groundbreaking discovery changed everything. A research team led by Harry B. Whittington and Derek Briggs found a nearly complete specimen. This fossil showed the shrimp arm, Anomalocaris, positioned directly in front of the jellyfish mouth, Petoia, and all of it was attached to the sponge body, Lagania. This single finding overturned all previous assumptions, forcing scientists to combine these fragments into one single organism. This consolidation was more than just a taxonomic adjustment. It was a revolution in paleontology. It debunked a popular view at the time that the Cambrian was an evolutionary explosion that created countless novel, now extinct animal phyla. Instead, it showed that the morphology of Cambrian animals was far more complex and distinct than previously imagined. Today, Anomalocaris is classified as a member of the order Radiodonta, a stem group of arthropods, distant relatives of modern-day insects and crustaceans. When reconstructed, Anomalocaris appeared as a perfect biological machine, optimized for a predatory lifestyle. Its size, approximately 14 to 15 inches long, and even larger in some other species, was gigantic compared to other creatures of its time. However, previous estimates suggesting it was up to 3 feet long may be inaccurate. One of its most notable features was its large compound eyes, set on short stalks. Eye fossils found in Australia show that each eye had more than 24,000 independent lenses. This number is comparable to the vision of a modern dragonfly, 28,000 lenses, one of the insects with the best eyesight today, and is 30 times better than a trilobite's. This gave Anomalocaris a superior advantage in spotting and tracking its prey. Its pair of front appendages were its primary weapons. They were flexible, segmented structures with sharp spines on the inner surface, like trapping gloves used to grasp prey. Right behind the front claws was its strange conical mouth, called an oral cone. This structure consisted of a ring of plates arranged in a tri-radial pattern, with 3 large plates and many smaller plates surrounding a central opening. The body of Anomalocaris was flattened and streamlined, with 13 pairs of soft flaps on either side. It moved by undulating these flaps in a wave-like motion, from front to back, generating efficient propulsion. Simulation studies have shown that this swimming method was extremely stable, allowing it to swim fast and maneuverable without needing a complex brain for balance. The combination of these anatomical features not only confirmed Anomalocaris as a predator, but also revealed that an evolutionary arms race had begun very early in the Cambrian period. The emergence of a species with superior vision, fast swimming speed, and grasping limbs created a strong selective pressure on other species, pushing them to develop protective features like hard exoskeletons, similar to trilobites. This shows that Anomalocaris was a key evolutionary driver of its era. For decades, the popular view was that Anomalocaris was the trilobite terminator. This hypothesis was supported by evidence of circular bite marks on trilobite fossils that fit its mouth. Additionally, fossilized feces, coprolite, believed to belong to Anomalocaris, also contain trilobite shell fragments. However, science is a continuous process of updates. Recent research has sparked a heated debate about the creature's diet. Biomechanical studies using computer models suggest that Anomalocaris's front limbs were too weak, lacking the force to break the rock-hard shells of trilobites without being damaged themselves. Analysis of its mouth also showed few signs of wear, and its structure suggested a better ability for suction rather than biting. This led to a new hypothesis. Anomalocaris may have been a hunter in the open water column, using its speed and vision to pursue more soft-bodied, agile prey, such as worms. This debate illustrates that science is not a static story, but a continuous process that is updated and adjusted based on new evidence. The initial hypothesis of the trilobite terminator, while dramatic, is being replaced by recent evidence that paints a more complex and subtle ecological picture of the Cambrian Ocean. The Cambrian period ended, but the story of Anomalocaris did not have a happy ending. While many other species, particularly trilobites, survived multiple extinction events and persisted for hundreds of millions of years, this massive creature and its relatives gradually weakened and disappeared. Evolutionarily, Anomalocaris belonged to the Radiodonta, a branch that split off from the arthropod family tree very early. It is the closest relative of today's arthropods, like insects, shrimp, and crabs, but is not their direct ancestor. It was like a branch that veered in a different direction, reached its own peak, and then faded away. Anomalocaris was a great predator, but it wasn't alone. It was just the most famous member of a massive dynasty, a lineage that once dominated ancient oceans. The order Radiodonta. This group branched off from the arthropod family tree very early and became one of the most successful lineages of the Cambrian period, with many members even more astonishing in size and shape than their famous cousin. Take a look at Titanocris. At up to 5 feet long, it was one of the largest animals ever found from the Cambrian. But what truly makes it stand out is its massive helmet-like head shield, which made up a full 2/3 of its body. This broad, flattened carapace made it look like a mothership hovering over the seabed. Scientists believe Titanocris was a benthic predator, using its rake-like front claws to sift through sand and mud to find hidden, soft-bodied prey. And then there's another relative, Cambrian, which had the bizarre look of a strange spacecraft. Its broad horseshoe-shaped head shield earned it the nickname the spaceship. Like Titanosaurus, it had front appendages with evenly spaced spines, thought to be used for sifting through seafloor mud for food. The sheer diversity and size of creatures like Anomalocaris, Titanosaurus, and Cambrian proved that Radiodonta was not a random evolutionary offshoot or a lone freak. They were a successful and diverse lineage, a pinnacle of Cambrian biology, equipped with the most powerful survival tools of their time. And that very success makes the story of their eventual extinction all the more tragic. There are several theories about its extinction. One is the ecological trap. Being overly specialized in one type of food could have become a major disadvantage when the environment changed or food sources dwindled. Additionally, environmental shifts, such as changes in sea level or the chemical composition of the ocean, may have been detrimental to Anomalocaris and its relatives. The appearance of new predators, faster or with more efficient evolutionary traits, may have also outcompeted Anomalocaris. The different fates of Anomalocaris and trilobites offer a profound lesson about evolutionary adaptation. While Anomalocaris was the most powerful predator of its time, the resilience of trilobites with their hard armor, a feature driven by their relationship with Anomalocaris itself, helped them survive much longer. This shows that in the evolutionary race, flexibility and long-term survival are often more important than being the strongest at a specific moment in time. The journey from a misidentified fossil fragment to one of the most incredible creatures ever known is a testament to the power of science. However, despite what has been discovered, the mystery of Anomalocaris remains. We still don't know for sure what prey it hunted or why it went extinct. And could any of its descendants still exist in today's oceans? The story of Anomalocaris shows that the history of life is not a closed book, but a great unending detective story. Every fossil, every tiny trace is a clue. And that's why we keep digging. Thank you for watching. If you are fascinated by the mysterious world of prehistory, please hit the like button, share this video, and don't forget to subscribe to our channel so you won't miss our next explorations. Let us know what you think about Anomalocaris and the mysteries of the Cambrian period in the comments below. See you in the next episode.